Alright, so in the previous course we talked about resistors, and now we know that resistors are used to limit the current in a circuit, right? So let's imagine that we have this circuit and the light bulb requires 1 amperes in order to fully glow. We also have a power supply of 5 volts, and the question is, how do we use a resistor, or a better question might be, what value of the resistor should we use in the circuit in order to set 1 ampere of current to flow in the circuit? In this course, we will start talking about Ohm's law, then we will do an experiment with it. We will move on to measuring power across a resistor, where we will define an equation used to measure the power dissipated by a resistor in a circuit. After that, we will define the equation to calculate the total resistance when resistors are placed in series or in parallel. So in this course, we will define some important equations that you have to know, and without further ado, let's get started. As I probably already mentioned, Ohm's law is the bridge between voltage and current. Combining the elements of voltage, current, and resistance, Ohm's developed the following formula, where V is voltage in volts, I is current in amps, and R is resistance in ohms, and this is called as Ohm's law. Now let's say, for example, that we have a circuit with the potential of 1 volt, a current of 1 ampere, and resistance of 1 ohm. So using Ohm's law, we can say that 1 volt is equal to 1 amps times 1 ohm. Now let's say this represents our tank with a white hose. The amount of water in the tank is defined as 1 volt, and the narrowness, in other words, the resistance to flow of the hose, is defined as 1 ohm. Now using Ohm's law, this gives us a flow of current of 1 ampere. Using this analogy, let's now look at the tank with the narrow hose. Because the hose is narrower, its resistance to flow is higher, right? So let's define this resistance as 2 ohms. The amount of water in the tank is the same as the other tank, right? So using Ohm's law, our equation for the tank with the narrow hose is 1 volt equal to current times 2 ohm. Alright, but what is the current? Because the resistance is greater and the voltage is the same, this gives us a current value of 0.5 amps. The main takeaway of this water tank analogy is that the greater the resistance of the hose, the less amount of water, in other words current, will flow through it. And now it's time for us to do an experiment. For this experiment, we want to use a 9 volt battery to power an LED. LEDs are fragile and can only have a certain amount of current flowing through them before they burn out. In the documentation of an LED, there will always be a current rating, and this is the amount of current that can flow through the particular LED before it burns out. Just a little side note before we proceed, LEDs are what's known as non-ohmic devices. This means that the equation for the current flowing through the LED itself is not as simple as voltage equal to current times resistance. The LED introduces something called a voltage drop into the circuit, thus changing the amount of current running through it. However, in this experiment, we are simply trying to protect the LED from overcurrent. So we will neglect the current characteristics of the LED and choose the resistor value using Ohm's law in order to be sure that the current through the LED is safely under 20 milliamps. Alright, so for this example, we have a 9 volt battery and a red LED with a maximum current rating of 20 milliamps or 0.02 amps if you prefer in this way. And to be safe, we would rather not drive the LED at its maximum current, but rather a slightly lower current, let's say 18 milliamps. If we simply connect the LED directly to the battery, the values for Ohm's law look like this. So the voltage is equal to current times resistance, and therefore the current is equal to voltage divided by resistance. And since we have no resistance yet, the current will be equal to 9 divided by 0. And dividing by 0 gives us infinite current. Well, not infinite in practice, but as much current as the battery can deliver. And since we do not want that much current flowing through our LED, we are going to need a resistor. Our circuit should look something like this. Now we can use Ohm's law in the exact same way to determine the resistor value that will give us the desired current value. So again, the voltage will be equal to current times resistance, and therefore resistance will be equal to voltage divided by current. And by plugging in our values, the resistance will be equal to 9 volts divided by the desired current, that is 0.018 amps. And solving for resistance, the resistance will be equal to 500 ohms. So we need a resistor value of around 500 ohms to keep the current through the LED under the maximum current rating. Here's what our device looks like all put together. Success! We've chosen a resistor value that is high enough to keep the current through the LED below its maximum rating, but low enough that the current is sufficient to keep the LED nice and bright. Many folks learning electronics for the first time struggle with the idea that a current limiting resistor can live on either side of the LED and the circuit will still function as usual. So to make things a little more complicated, you can place the current limiting resistor on either side of the LED and it will work just the same. When an electrical current passes through a resistor due to the presence of voltage across it, electrical energy is lost by the resistor in the form of heat, and the greater this current flow, the hotter the resistor will get. And this is known as resistor power rating. Power is usually calculated by multiplying voltage and current, but by applying Ohm's law, we can also use the resistance value in calculating power. If we know the voltage across a resistor, the power can be calculated as voltage squared divided by resistance. So if we know the current running through our resistor, we can calculate the power as current squared times resistance. So you can choose from these two equations to calculate the instantaneous power across a resistor. Again, this is instantaneous power. It's the power that the resistor dissipates in a certain moment in time. For average power, you must take the time average of the squared voltage and divide by the resistance. When you are dealing with circuits, you will often see resistors connected in series or in parallel. When connected in series, resistor values simply add up. The total resistance is the sum of all series resistors. So for example, if you just have to have a 12.33 kilo ohm resistor, seek out some of the more common resistor values of 12 kilo ohm and 330 ohm and connect them together in series. Alright, so this is how you calculate the total resistance when the resistors are connected in series. On the other hand, finding the resistance of resistors in parallel isn't quite so easy, but not that hard either. The total resistance of n resistors in parallel is the inverse of the sum of all inverse resistances. This equation might make more sense than the last sentence. So in order to find the total resistance, invert each resistance value, add them up, and then invert that. Yeah, I know it's kinda weird. As a special case of this equation, if you just have two resistors in parallel, their total resistance can be calculated with this slightly less inverted equation, where the total resistance is equal to R1 times R2, all divided by R1 plus R2. As an even more special case of the equation, if you have two parallel resistors in equal value, the total resistance is half of their value. So for example, if two 10 kilo ohm resistors are in parallel, their total resistance is 5 kilo ohm. A shorthand way of saying two resistors are in parallel is by using the parallel operator. So for example, if R1 is in parallel with R2, the conceptual equation could be written as R1 in parallel with R2. A much cleaner and hides all those nasty fractions.